Since it's been a while since we've met, I wanted to do a quick review of some chemical kinetics, and in this case we're going to review some things about reaction rates, and then a little bit about rate equations, and primarily determining rate equations using the method of initial rates. I'm going to work problems. I needed an example, so I'm taking problems from a book, Chemistry, by Riddell and Navidi, from West Publishing in 1990. It's a book that I had on my shelf. So we'll do a couple of review problems here to help you knock the dust off of your basic chemical kinetics. Okay, so our first reaction is it's the Hubbard Oswald process for oxidizing ammonia to make nitrogen oxides. It's an important process in eventually making fertilizer from ammonia. So we've got this reaction where ammonia is reacted with oxygen to make nitrogen monoxide and water, all in the gas phase. And so they give us an equation for the reaction rate. And so say someone has studied this reaction and they have used this as their definition of rate, right? Change in concentration of the product nitrogen monoxide with change in time, okay? Now if we look, right, since this is molarity, we could also express that as, let's go with color we can see, equals the change in moles of nitrogen monoxide. And if we're assuming the volume of the container isn't changing, then liters and time would be the same, right? And so if we look at it that way, it makes it easier to see stoichiometry, I think. So the question is, say we're communicating with groups that are studying the other components. Can we convert change in concentration of nitrogen monoxide with time to other units so that we can communicate with other groups? Okay, so let's start with ammonia, right? That would be straightforward. And we can use the stoichiometry here, right? So from the stoichiometry, we know that 4 moles of ammonia react every time 4 moles of nitrogen monoxide is formed, right? And the 4's cancel, and so the rate should be the same, right? And moles of nitrogen monoxide cancels, the 4's cancel, and so we get change in concentration of ammonia. So I'm running out of space here. Change in concentration of ammonia with time, right? The rates would be the same, the difference being that ammonia is disappearing as nitrogen monoxide is appearing, and so that would have to have a negative sign because ammonia is disappearing, right? We have to remember how we defined our rates. So the rate of change in terms of ammonia is the negative of the change of concentration of ammonia with change in time. But the absolute value of that rate would be the same because the stoichiometries are even, okay? So now if we take this again, stop it, our change in moles of nitrogen monoxide per liter per time. And if we go to oxygen, right? Then we go that there are 5 moles of oxygen reacting, and that's going away, for every 4 moles of nitrogen monoxide that's produced, okay? And so, right, our moles of nitrogen monoxide cancel, but our ratio in this case doesn't cancel. So to express this answer in an equivalent unit, it would be minus 5/4 times the change in concentration of oxygen with time. That would give us an equivalent measure of the rate that we could compare. Okay? And if we do the same thing with water, let's start it again with this, right? So our change in moles of nitrogen monoxide per liter per time. And we're going to multiply that times plus 6 moles of water, because we're making it, and plus per 4 moles of nitrogen monoxide that we're making, right? So moles of nitrogen monoxide cancel, right? And so we're going to get 6/4 times the change in concentration of water over time, okay? And if we reduce that, it would be 3/2. Really bad bracket. Okay? So we can use our stoichiometry. It's one of the reasons why we learned stoichiometry in the first semester, to relate the rate of, one thing, if it's given in one set of units, to anything else in the reaction. That's something you probably need to practice. Okay? Now, the other thing we wanted to look at was a method of initial rates problem, right? So here we have, a generic reactant, 2 generic reactants, A and B, reacting to make some product. And we set up individual experiments, experiment 1, experiment 2, experiment 3, where we set an initial concentration of A and an initial concentration of B and measure the rate immediately after we mix the two, right? That initial rate estimate. And so we did that 3 times. Okay, now, so in this, we know that this reaction is going to follow this equation. What we don't know is what A and B are, and then ultimately we want to know what K is as well, right? And if we remember, right, in our method of initial rates, if you divide initial rates, right, so notice, for instance, in these first 2, B is the same, right? And the rate constant should be the same. So if we take rate 1, right, and rate 2, and divide them, right, then K should cancel. K divided by K is 1. And since the concentration of B is the same, and this exponent is the same even if we don't know what it is, then the B's will cancel. And so that isolates the rates and the thing that is different, that is A. And so we get something that looks like this, right? So rate 1 would be 0.012 molar per liter per second. I'm going to leave the units off because I'm sort of tight in space here. And then we've got 0.1 108, same thing, but because we're dividing, the units will divide out. And it's going to equal our concentration of A, which is going to be 0.10 raised to the A, and 0.30 raised to the A, right? But because those A's are the same, that's the same as 0.10 divided by 0.30 all to the A. And so if we do the math, and I'm taking my calculator out now, so if I take my 0.012 divided by 0.108, I get 0.111, and that's extending. And that's going to be equal to, right, 1 divided by 3 is going to be 0.333 to the A. Now, if we want to bring the A out, then we take the log. So our log of 0.111 is going to be equal to A times the log of 0.333, right? So A is going to be equal to the log of 0.111 divided by the log of 0.333. Did I get that right? Let's see. We'll find out. And if we do that, we get A equals 2, right? So that means now we know that A equals 2, okay? Now that we know that A equals 2, right, we can find, we have A. We do the same thing for, right, note in the first one and the third one. A is the same, but B is different, right? So we do the same thing with rate 1 and rate 3. And if you do that, you will find that B equals 1. And now that we know A and B, we can take any of our data and find K from the rate. And so we should be able to find K as well. Okay? Okay, so to continue that last problem and find K and its units, so now we know that this is the form of our rate equation, right? That our rate is equal to K times the concentration of A raised to the second power, concentration of B raised to the first power. And so we can take any one of those experimental points and solve for K, right? So if we're doing our work here, then our rate is 0.108, and that was molar per second, okay? Right, so that's 0.108 molar per second is equal to K that we don't know. Our concentration of A is 0.30 molar, and that's squared. And our concentration of B is 0.60 molar, and that's squared, right? No, I take that back, right? That's to the first power, okay? I have to remember that, okay? So our 0.108 molar per second divided by 0.30 molar squared, 0.60 molar equals K, which is equal to, give me just a second. Okay, so that comes out being equal to 2, and then we've got molar. We have to keep track of our units here, right? So we've got molar in the denominator and molar squared times molar cubed in the denominator. So that's going to be per molar squared, and then our time second is, or our time unit is still in the denominator. And so that our rate constant would be 2 per molar squared per second. Okay, so I hope that helped you remember how to do the method of initial rates and how to look at comparing rates across a reaction.